So 3.2 is going to be a continuation of the functions that we talked about in 3.1. More specifically, we're going to talk about linear functions. Anyway, so our vocabulary-wise, the first linear equation in two variables. Those two variables are typically going to be x and y. So if I can get my pen to work here. So that is going to be, it is an equation. That can be written as y equals mx plus b. Okay, so again, the key is x to the first power and y to the first power if we're going to have a linear equation. Now, a linear function is going to be a non-vertical line that has a constant rate of change. So therefore, if we're going to flip over to nonlinear, non-linear functions do not, or does not, have a constant rate of change. Again, so that constant rate of change means it's going to go up to and over 1, or up to and over 1. So we're going to continue to find that path. So it's going to make a straight line. That's what a linear function is. It makes a straight line. Okay? A non-linear function is going to be that, a quadratic function, because I don't have the same rate of change. It is not going up and down, up and over, down and over at the same rate throughout the graph. So therefore, it's non-linear. Okay? Solution for a linear equation in two variables. It is going to be an ordered pair that makes the equation true. So when I graph something like, we'll start out with y equals 2x minus 1. So we'll get into graphing with slope and y-intercept later, but for right now, I'll just graph it for you. This is the process it's going to take, and so there's the linear function that is represented by y equals 2x minus 1. And if I take that ordered pair of 0, negative 1, and I put that into my equation, my y value is negative 1, my x value is 0, I end up with negative 1 equals negative 1, so that made it true. If I take another point that's on that graph, it was 2, 4, it looks like. Nope, 2, 3. So if I look at that, again, if I plug those in, there's 3 equals 2 times 2 minus 1. So I end up with 3 equals 3, so that's true. So again, a solution is going to be, that's what a line is. If we graphed a line is a graphical representation of all the solutions for a given equation, and in that case, it was that. Okay? Discrete domain. Again, the domain is your set of inputs. So it's a set of inputs that are discrete, meaning is only certain numbers. So, for example, a discrete domain would be something like 1, 2, 3, and 4. So my domain is specifically those integers. Okay? Whereas a continuous domain is the set of inputs that is an interval. So I could have the domain be anywhere from 1 is less than or equal to x, which is less than or equal to 4. So those two are very similar in nature. However, a number like x equals 2.5 is not in this one, okay? However, it is in this one, because 2.5 fell right between two numbers there. It's not in my domain at all, okay? Whereas 2.5 would fall in between 1 and 4. 2.5 is going to lie in between 1 and 4, so that's why it lies there. So again, a continuous domain versus a discrete domain, and we'll just talk our way through those when we get there, okay? So again, we're going to go back to functions, a review of function. Each x has its own y, so we can see that negative 1 is mapped onto 2, 0 is mapped onto 3, 1 is mapped onto 4, 2 is mapped onto 5. Now what we're worried about today is going to be, we're going to add linear to it. Okay, so we can see that this, I can see that my rate of change here, over here, I went up 1, I went up 1, and I went up 1. This also went up 1, up 1, up 1. So in that particular spot, we have a constant rate of change, so that is good. We have the same exact mapping, and over here we have a graph of that, and we can see, again, my graph is very linear, okay? It forms a straight line. Discrete and continuous domains. So again, I went 1 through 4, didn't realize it, but 1 through 5 is what the example shows. So integers 1 through 5 are going to be those specific points, where a continuous domain is going to be all numbers. Okay, discrete domain is just integers. A continuous domain is all numbers. So 2.5 would be part of my domain there. Okay, so in reality, there wasn't a whole lot to these notes whatsoever, because this is going to be our independent practice, our practice. Okay. So we're going to look at a graph, and we're going to determine, is it linear or non-linear, okay? And basically, does it form a straight line or not, okay? Or basically, the straight line means it has a constant rate of change. Okay, so and this one is non-linear, because here it went up 1 over 1, but then here it went up 1 and over 3, and so I have a different rate of change for different intervals as far as on the number line, okay? In that particular sequence of numbers here, we went up 1 and over 4, we went up 1 and over 4. So again, it has a constant rate of change, okay? So this one is linear. It has a constant rate of change. Table-wise, is it linear or non-linear? I kind of went through the one up above. We're going to see my x value increases by 1, increases by 1, increases by 1. My y value increases by 3, increases by 3, increases by 3. So therefore, this is linear. Constant rate of change. If we come over here, this goes up by 1, it goes up by 1, and it goes up by 1. So my x value is changing constantly. However, my y is going to go down 1, it's going to go up 1, and then it's going to go up 3. So there is no constant rate of change. So this is non-linear. There is no constant rate of change. An equation. We really didn't get into what causes the equation to be linear, but really it's paired up with x and y. So when x is the first power, y to the first power, I can just automatically go with linear on that, just because. If we would, we might strike this into a graphing utility, and if we did that here, we would see something that looked like that. And so we can see then it is a non-linear system. There is no constant rate of change. I would say that would be the easiest, if we could find a graphing utility. Otherwise, we're making a t-chart, or again, we would look for the key term there. We have x to the third, which makes that non-linear. Okay, and then lastly, again, we have discrete and continuous. We have to find the domain of each function and then describe it as discrete or continuous. So again, my domains are on my x values. So I'm looking at my x-axis. Okay, I have x values that go from here at 1 over to here, 5. So that is my domain. But in this case, I have to know, am I going to write this as an interval, or is this going to be a set of points? And this one's going to be an interval. So 1 is my left-hand boundary, 5 is my right-hand boundary, X is going to be somewhere in between. They are filled in circles, so it's greater than or equal to, less than or equal to. So there's my domain. And because I have all the points in between, meaning 1.5 is a possible domain, this makes this one continuous. Okay, over here on this one, my domain, again, all my possible x values I have here and I stop here. So that's 1 to 3. However, they are specific dots on my coordinate plane. So this is the set of points. 1, 2, and 3 is going to be the domain, okay? And so because it is specific points, 1, 2, and 3, specific integers, that is going to make it discrete. And we have conquered this set of notes. All right, that went fast.